Last night of new material. And let me share the screen real quick. A couple things I want to go over with you before we go over that material. So just a reminder, you have 3 sections of homework due tonight, 8.1, 8.2, and 8.3, and then the Unit 5 test. And that's the last My Math Lab assignments in the course, other than the Proctored Final, okay, which you'll start taking next week. It'll open up on Monday, 12:01 a.m. through Wednesday night. And if you want to continue to rework any My Math Lab homework, that'll also be due next Wednesday. I'll remind you of that when I send the message out tomorrow with your updated grades. I have a couple problems I picked from these sections for tonight that are due tonight, a couple to go over with you. Now, it looks like a lot of stuff that we're going to do tonight, but the first 3 sections all go together because they're on correlation and regression, and I think they go nicely together. In the normal semester, we do those in 1 week. I'll talk about the class next week. Hold on just a second. And then 11.2 is kind of the oddball section. Then we'll do that, but it goes along with what's in here because it's all looking at data, 2 variables collected on the data. So I call it count data. This is count data, and then this is quantitative data. Okay, so next week I will have class. So if anybody has questions before they take the Proctored Final, I will be here. We don't have any new material. Oh, actually, I thought next week, if you want, even though you can already take the final, we can go over a copy of the proctored midterm. I mean, of the preparation quiz if you want. That's up to you.
That would be great.
Okay, that's fine. You know, the proctored exam will be available till Wednesday night, so you'd still have time to do it. So, and I will post a copy of that. And I wanted to remind you of a couple things. Let me go into, get the My Courses course up here. Oh, got too many windows open. All right, let's go back over here. So the SSI lady, well, I didn't do my SSI, so I keep getting the message. What did I want to remind you in here? I can't remember now. I don't remember what I was going to talk about in here. You actually made your numbers. So I had updated this right before class, but then Derek put a submission in, so we actually hit the 40. So you have your extra credit point. And I will add that to the grade book in the morning. I thought there was something I wanted to talk about in the course, and I can't remember what it was. My mind just went blank. Okay, lots of people are still coming in. Okay. All right, well, while we're here, let me go back over to my stat lab because there were a couple of problems that looked like they were a little harder, or at least they took people more time to get correct. So let me show you the ones that I picked to go over. And if there's any others that you want to do, we can go through those. So in 8.1, you did pretty well in 8.1. The only one I saw that might have been a little trickier was problem number 12. So let me get problem number 12 up here. And I think it might be because of the wording of the problem. So it said, now this one changed from when I ran it before. When I did it before, it said a minority, but this time the question is saying a majority of adults would erase all of their personal information online if they could. A software firm survey of 483 randomly selected adults showed that 63% would erase their personal information online if they could. Express the original claim in symbolic form. So the first thing you want to think about, because it's going to be important on the test tonight, are we talking about proportion or are we talking about a mean? So what are we talking about in this problem? Proportion or mean?
Proportion.
Proportion, yeah. So your drop down here, we don't do anything with sigma, so you're never going to have that as an answer. We're always going to do proportion or mean. Now we want to do the claim, the original claim in symbolic form. The claim was a majority. How do I write that as a claim? What does majority mean? More than, so it's going to be more than something, more than what? What's a majority mean? Is 40% a majority? Nope. Has to be more than what to be a majority?
0.5.
0.5, yes. Right? Because it's got to be majority. If you're going to win by majority, you have to have 50% plus 1 actually in an election. So we're going to check the answer. And then the second part of the question just asked you to write the hypotheses. And I don't know if the first part was just a little confusing because it was talking about writing the claim. So remember, you're going to put P in both here. So I put in the P first. Oh, I got to get all my Zoom windows out of there. Oh. And then this one. Now, remember that null always has the equal in it. Now, where's this claim going to go? It's going to go into the alternative, right? Because that's what we're trying to prove. So we're going to put in the point greater than 0.5 here. And my null is going to be 0.5. And you know what's nice in Statcrunch is once you enter that number into the one hypothesis, it automatically puts it in the other one, which is kind of nice. You have to remember to do that when you're working on my stat lab problems here, my math lab problems rather. Okay, so I'm not sure if it was because the first part was on the claim. I don't know. I don't think it was any more difficult than any of the other ones, but are there any others in 8.1 that anybody wants me to go over? 8.1. Okay. All right, if not, I'm going to go up to 8.2 and I'm going to do a couple problems from 8.2. So in 8.2 is where you were actually doing the hypothesis testing on the proportions. So I picked problems, whoops, number 5. These are all kind of the same. So I think if I do 1 or 2, I think it will give you an idea of how to do them. So number 5 was the first one I picked. Now this one had output, and I know we went over one like this last week. This one has all the work done for you, and all you're going to do is read off of the output to answer the question. So it says a certain drug is used to treat asthma. In a clinical trial of the drug, 18 of 261 treated subjects experienced headaches. The accompanying calculator, this is if you were doing it on a TI 83 or 84, shows the result of a test of the claim that less than 11% of treated subjects experienced headache. And you see that claim right here. As proportion less than 0.11. That's the alternative hypothesis. There's your test statistic, and there's your p-value, and there's actually your sample estimate right there, your point estimate from the sample, and there's your sample size, 261. So is the test two-tailed, left-tailed, or right-tailed? So here's your alternative. Is that two-tailed, left-tailed, or right-tailed? That's going to be left-tailed, right? Because it's a less than, so it's going to be on the left-hand side. And then they want to know, I think they want to know the test statistic, which is right here. And we're always going to do 2 decimal places for test statistic. So it's negative 2.12. Negative 2.12. And then they want the p-value, usually 3 or 4 decimals. They want 4.1706. So again, this is kind of an easy one because they did all the work for you. You're just reading the answers off of the information they gave you. And then they probably want you to interpret it. Oh, where's my continue button? Oh, I didn't check it. Okay, check answer. Okay, we got that one. And now, oh, I got it wrong, I guess. Wait a second. I can't see. I've got all this. You guys don't see all the Zoom tools we have here, but I guess I got it wrong. Oh, what did I do wrong? Hold on a second.
It's because you didn't, when you put the,
I put an extra 0. I missed a 0. I apologize. See what I did? See, your teacher made a mistake. Yeah, I want to leave that one. Let's go back for a second. I put in 0.17. Shoot, where's that problem? Not number 5. I put in 0.17 and it was supposed to be 0.017. My fault. Okay, and I showed it to you. I just wasn't reading it right there. It is right there, 0.0171. Okay, so that was just using output that was given to you. And we did go over that last week. Okay, and then, wait, we're supposed to have hypotheses. We're not done yet. There's more parts to this one. Hold on a second. Yeah, wait a second. I got to get to the rest of the parts here. Oh, I went to
scroll down.
Yeah, I didn't scroll down. Okay, I know there's more parts to it. There we go. This one has a lot of parts because it's worth 6 points. What's the null and what do you conclude about it? Okay, so you wanted to test the claim. So here's your claim. It's less than 11%. So your null is going to be what? That it is equal to, right? Because we always have an equal sign in our null. And now our decision. Okay, so our p-value was 0.0171, and we're using a 0.05 significance level. Are we going to reject or fail to reject? Is 0.0171 less than 0.05? Yes. So we're going to reject. Reject because the p-value is less than or equal to the significance level, which is this answer here. And enter, and you're done. I think that's it. No, one more. What's the final conclusion? Okay. So if we reject, we say we have sufficient evidence to support the claim, and the claim is in the alternative, so we can talk about it. To support the claim that less than 11% experience headaches. It's right there in answer A. Because the other one says sufficient evidence to warrant rejection of the claim. No. We're supporting that claim because it's in the alternative. We always like to put the claim in the alternative if we can. Because if we reject the null, then we can say, just like we did here, that we can support that claim. Okay? If it was a not equal to, then we can talk about this warrant rejection of, and that's why we don't like to have it in the null. We'd rather have the claim in the alternative if we can. All right. That was number 5. And then I also picked, oops, I can't find my other problem. What other one did I pick? Number 13. Let's see. Number 13. Come on. Oh, I guess, no, hold on a second. Why can't it want to go ahead? Hold on. Let me do it this way. I thought I had to. Come on. There we go. All right. Okay, so for this one, we have a random sample of births that included so many boys. Use the 0.05 significance level to test the claim that 51.3% of the newborn babies are boys. Okay, so this is one of those examples where the claim is going to end up where? In the null, because that claim is that the number is equal to this. All right, so I can eliminate answer B because the null is not written correctly. It has to have an equal sign in it. So I'm left with A, C, and D.
D.
What's the right answer?
D.
D.
D. Yep, because my alternative is just not equal to. It didn't tell me a direction. It doesn't say, do I think there's more than or less than? It just says, is it equal to? So it's a not equal to. So it's a two-tailed alternative. And then we want to do the test statistic. So what are we going to do? We're going to use Statcrunch. And we're going to go to Statcrunch. And we're going to go to stat, proportion stats, stat, proportion stats, one sample with the summary. Remember, everything you do on proportions is with summary. So we have 433 boys. They're the successes out of 856. And we're testing equal to 0.513 versus not equal to. Okay. And then I just go ahead and I compute. And so let's see, what are they going to ask me for? The test statistic first, right here. So it's going to be negative 0.42. I think pretty sure that's what I'm going to ask for first. Yeah. Oops. Negative 0.42. And then they're going to ask me for the p-value, which was right next to it. This time they want 3 decimal places. So let's go back to our Statcrunch here. So 3 decimals, 0.675. So start thinking about whether you're going to be rejecting or failing to reject this time. Okay. So what's my conclusion? My significance level they picked was 0.05. So with this p-value, am I going to reject or fail to reject is my first question. Is this p-value less than 0.05? Right here. Is 0.675 less than 0.05?
Negative, it's more.
It's more, right? So we fail to reject. So we're going to go between answer A and C. So A says there is sufficient evidence to warrant rejection of the claim. We fail to reject, there's not sufficient evidence. So we're going to go with C. Okay, see the difference, a little bit of the wording too, when it's a not equal to alternative, it's a little tiny bit different. And I know that's a little confusing for students.
That wording is the one thing that threw me off during the test. Something serious.
Well, yeah, you're just going to have to get, if it's a not equal to alternative, that's where it gets tricky. When the claim is in the alternative, it's really easy to answer, figure out the, the conclusion. This is where you have to remember when you have a not equal to, you're going to talk about sufficient evidence. You're not just going to say to warrant rejection of the claim, because the claim here is in the null and you can't accept the null. I mean, you can't do that. So do these results support the belief that 51.3% of newborn babies are boys? Okay, so let's look at the answers. The results support the belief that 51.3% of newborn babies are boys because there was sufficient evidence to show that this was true, but we just said there wasn't sufficient evidence, right? The results do not support this belief because there was sufficient evidence to believe it's untrue. Bad answers. The results support the belief that 51.3% because there was no evidence to show it's untrue. That looks pretty good, C. But look at D. The results do not support the belief that 51.3% of newborn babies are boys. The results merely show there is not evidence against the rate. So which answer do you think is better, C or D?
Would you go? You would go with D, correct?
Yeah, D is better because if you think about it, we can't, there's not evidence against it. We didn't reject it, but we don't really support it because we can never say we accept the null. Let's check and make sure. But yeah, D is a better answer because you can't, when it's a not equal to and you fail to reject, you haven't proven the null. You're just saying, I don't have any evidence to say it's not true. So we don't have strong evidence against that number. And that, again, that's why statisticians really like the claim to be in the alternative, because if I reject it, I can say, ah, there it is. That's what it is. I support the claim. It's in the alternative. But yeah, this is a better answer. C is not an incorrect answer, but D is a better answer. Okay, are there any others on 8.2? Those are the only two I picked. Let me just see. Yeah, those are the only two I picked. Are there any others anybody wants to go over? Now's your chance.
Can you do number 8?
Uh-huh.
Can you do number 8?
Yeah, I'm going to do 8. Somebody's got their audio on, and it's really given a lot of feedback. I don't know who it is. Okay, thank you. I'm not sure who it was, but we were getting a lot of reverberation. Okay. I did this one in class. Consider a drug that's used to prevent blood clots in certain patients. In clinical trials among a big number of patients treated with the drug, so many had the adverse reaction of nausea. Use a 0.01 level to test the claim. Again, here's one of these ones with, claim's going to be in the null, which I hate, just like the other one. So what are going to be our null and alternative here? We're trying to test a claim that it equals 3%. So I can eliminate C, it can't be C. So it's between A, B, and D. Which one's the right answer? Null is always equal to.
B.
B.
Yeah, it's B. To do, yeah, this again, this is going to be the same con we just had that you guys don't like. Test statistic. Okay, so we need to go to Statcrunch. Do I still have a Statcrunch window open? Oh, I do. Good. Okay. We'll just go ahead and edit this one. So we have 164. Not very many people got the nausea out of 5787. And we're doing 0.03 down here. 0.03 and not equal to, and compute. All right, so my test statistic is negative 0.74. Oops. So again, 2 decimal places. Oops, negative 0.74. And then the p-value, I forgot to look at it. What was it? 0.459. 0.45. Whoops. Not in the box. 0.459. Yeah, got it. And then what's your decision? And your significance level was 0.01. So is 0.459 less than 0.01 or greater than? Are we going to reject or fail to reject? We are going to. You got a 50-50 chance of getting it right. What do you think? Reject or fail to reject? 0.01 significance level. Here's my p-value, 0.459. 0.459 is not less than.
Fail to reject.
Fail to reject. Excellent. Thank you. So is it A or B? Not sufficient evidence again, right? So it's going to be A. It's just like the other one. And then there's probably a conclusion one here. Does nausea appear to be a problematic adverse reaction? Yeah, we did this in class, I remember. Since the rate of nausea appears to be relatively low, right? Pretty low. It is not. 3% is pretty low. Okay, and actually in your Statcrunch output, it actually shows you what the point estimate is from that sample. Here it is, 2.8% of the people had nausea in that sample. So that's pretty low. Doesn't seem to be a really unusually high adverse reaction. All right. Okay, anybody else on 8.2 before I do? I think I just have 2 from 8.3. Anybody else want any from 8.2?
Thank you, Dr. Wyman.
You're welcome. Anybody else? Okay, so let's go to 8.3, and I picked 2 out of here. So this is on testing on means now instead of proportions. And the first one I picked was number 2. Whoops. Here we go. All right. Let me get my Zoom windows out of the way. There we go. Oh. Okay, I don't. No, that can't be right. Hold on a second. That can't be the right question. It's not right. It's not number 2. This is not the one I picked. I got to flip through real quick to see which one it is. It's about the video games. It's not that one. There it is. It's number 4. I don't know why I said number 2. It's this one, number 4. Okay, so the video games. 12 different video games showing alcohol use were observed. The duration time of alcohol use was recorded with times and seconds listed below. What requirements must be satisfied? Yeah, this is the one I did want to do. To test the claim that the sample is from a population with a mean greater than 75 seconds, are all of the requirements satisfied? Okay, what are the requirements that have to be satisfied when we're dealing with means? What do we have to have? Either the population is normally distributed or n is greater than 30 or both. Is that true? We have to have that? We do, don't we? At least one observation has to be above or below 75. That has nothing to do with it. We don't actually talk about individual observations with these. Random sample is always a great thing to have. We always like to do that. And the binomial conditions only applies for proportion. So there's 2 that have to be met on this one. And then it says, are the requirements satisfied? Which is why I picked this one, because it talks about a normal quantile plot. And so this is why we're going to work on this one, because we're going to do the normal quantile plot in Statcrunch. Let me make sure my other Statcrunch window is gone. Yeah, it is. Okay. All right, so let's go ahead and open this data set up in Statcrunch. And remember how we did the normal quantile plot. Graph, QQ plot, select the variable, and then make sure we pick the normal quantiles on the y-axis so it makes a nicer picture for you to look at. Oh, what do you think about that one? That doesn't look very good, does it? Does that look like it's normally distributed? Remember what it was supposed to look like, a nice random pattern around a somewhat straight line? That doesn't look very normal. And we can also check over here, we could do a histogram just real quick and see what that looks like. And we did this one last week, I think. There's an outlier out here for sure. Okay, so it doesn't look like it's normally distributed. So it says, no, the conditions for a binomial are not satisfied. There's not enough information to tell it's from a random sample. There wasn't enough information because they didn't tell us that. That's correct. But what about, and the sample size is less than 30, so we needed to check for normality, right? Okay, this one I did, again, they're throwing in the 75 seconds thing. It's just kind of a, you don't need to talk about that, but they do talk about it in the correct answers, I remember. The sample size is not greater than 30, does not appear to be a normally distributed, and there's not enough information to determine if it's from a random sample. This one looks pretty good. It's got to be that one, because we know their conditions. It's not from a normal distribution. We just saw that. So it has to be answer C. And they didn't tell us anything about random sample. Okay. And then I also picked number 11, problem number 11. Let's take a look at that one. Number 11. Okay, so students estimated the length of 1 minute without reference to a watch or a clock. I think we did this last week also. Use the O1 significance level to test the claim that these are from a population with a mean equal to 60. Another 2-sided alternative here. Assume the conditions for conducting the hypothesis test are met, so you don't have to check normality, and you do have a small sample size, but we're okay. Okay, so what's the right null and alternative? It's going to be D. Okay, because we're testing again a claim that it equals 60 seconds. And then we're going to need to open this up in Statcrunch. And this time we're going to go to stats, one sample with the data, because we have the data now. So select the data, put in your null and alternative. And that's all we do. A lot easier. You don't have to enter the mean and standard deviation and all. So where's your test statistic? It's right here. It's a t statistic. Remember we talked about this when we do tests on means, we're using the t distribution instead of the normal. So 2.46, 2 decimal places. And then they want the p-value, which is 0.027, 3 decimals. Now, we are testing at 0.01 significance level. So is 0.027 less than 0.01? It's not, right? It's greater than it. So therefore, are we going to reject or are we going to fail to reject? If the p-value is greater than alpha, then we must fail to reject. There is not sufficient evidence to conclude that the mean of the population estimates of 60 seconds is not correct. Yeah.
Wouldn't you reject? Because the p-value
No. 0.01 is the significance level and your p-value is 0.027. This would have, the p-value would have to be less than 0.01, have to be like 0.005 or something. This is greater than 0.01. If it was 0.05, we would reject.
Oh.
See, it's not
Oh.
0.05. Careful, yeah, it's 0.01. But this time we failed to reject.
Roger that. Okay.
Got it?
Thank you.
Yeah, just be
thanks,
careful.
Alfred.
Make sure you look at the significance level.
I was
Yeah.
looking at the test statistic before. That actually makes a lot more
Oh,
sense.
yeah. Yeah, no. And then it says it does not appear, or wait a second, it appears. Yeah, it appears as a group that they're pretty good at estimating 1 minute. Let me just make sure we failed to reject. There is not sufficient evidence to conclude that the mean of 60 seconds is not correct. Yeah, I think that's right. We get it. Yeah, we did. Yeah, I had to look through those couple things. Again, those two-tailed alternatives are really trickier when it comes to writing the conclusions because it's not sufficient evidence. I'm trying to scroll down to the bottom of it. So it fail to reject. When we fail to reject, you always say there's not sufficient evidence, and then you're going to talk about what it says in the null, but you can't conclude that it's not correct because you don't have evidence against it. And so therefore, because we couldn't say the mean was different from 60, these students are pretty good at estimating 1 minute. All right, and those are the only 2 I picked. Are there any others from 8.2 that you want to go over while we're out here? Don't forget on some of these, you do have problems where I don't remember which ones they are, but where you have to enter the mean and standard deviation. They give you the information. Let's see, this gives you output. This has got output in it too. Okay, so here's one here where they give you the sample size. Whoops. They give you the mean, they give you the standard deviation. So when you go into Statcrunch, you're going to go stat, proportion, t-stats, 1 sample with summary, okay, instead of having the data. And then you're going to specify your null and alternative. This time, though, they give you the summary data rather than giving you the original data. Okay, so 2 types with means, only 1 type with proportions. All right. And again, don't forget while we're out here real quickly, don't forget to do your final exam preparation quiz too, because you got some extra credit you can get from doing well on that one. So don't forget about that. All right, so let's go on to the material for tonight. Are there any other questions on 8.1, 8.2, or 8.3 before we go to the last unit that we're going to finish up tonight? All right. Okay, so here we go. Okay, so the last unit is going to cover 2 big buckets of information: correlation and regression, and then tests for independence, chi-square tests for independence. And the first part is actually 2.4 and 10.1 really go together because they introduce the concept of, first of all, paired data, what we call paired sample data. So all the observations that we collect data on, we collect data on 2 variables. And we can make a picture of the data in what's called a scatter plot. So we have a y-axis and a y-axis, and we look at, see what it looks like when we plot the data. If you remember, we did time plots before. They're sort of like a scatter plot, where we had time along the x-axis and then the variable along the y-axis. This time we're going to have 2 quantitative variables on all of our observations or units, whatever we're measuring on. And the scatter plot's the picture. Then there is a statistic we can calculate that talks about the relationship between those numerically. It's called the correlation, the linear correlation. And there's a linear correlation coefficient. So correlation is when one variable is somehow associated with the other variable. And if it's linear correlation, then we look at the scatter plot and we see a somewhat linear relationship. And again, the scatter plot or scatter diagram is the picture that we make. One thing important in here is if you have correlation, it doesn't mean causation. Okay, so just because two variables have some kind of relationship doesn't mean one causes the other. The only way you can really prove that is to do an experiment. So you want to be careful about trying to make that conclusion. So let's take a look at what kind of associations we might see. So here is a scatter plot. We've graphed two variables, x and y, and we see here a nice pattern. As x is increasing, y is increasing. So we say this is positive association or positive correlation. Positive linear in this case because it actually does appear to follow a straight line. Here's a negative association. As x increases, y is decreasing. And here's no association. We call this just a random pattern. There's nothing going on. As x is going up, y could go up or down. There's nothing going on there. When you're working on a problem with two variables, you want to make sure you make a picture first so you can see whether or not you do have a linear relationship. So when we look at a scatter plot, the things we look at, is the association linear? So here's a somewhat linear. It's not going to be perfect, but as x is increasing, y is increasing. Okay. Here's something that's associated, but it's not linear. It's actually a parabolic relationship. Here's another one. This is an exponential relationship. If you graph your data and it looks like this, you can't apply the methods we're going to talk about tonight because they're going to assume a linear relationship. Then we talk about strength. So we talk about first the association. Is it linear or not? And then how strong is it? So this one's very strong. If we were to put a straight line on that graph there, the points are tightly clustered around that line. This one's also strong, but it's not linear. This is what we call a weak to moderate association. You're probably going to look at that and say, I don't see anything. But there is a trending there. As x is increasing, y is tending to also increase. This one has no association. The other thing that we look at on a scatter plot is, are there outliers, gaps, or unusual features? So here is an outlier. It's far away from the other values, but it's also in the same linear relationship line, if you notice that. So it happens to just be a value that has a high x and a high y value, but it looks like it may have the same relationship that we see with the lower values of x and y. Here's some gaps. So by gaps, we've got a bunch of points here. We've got a point stuck here. We've got a point stuck here. There's a big gap here in the graph. Here's a huge gap with clusters. So in this one, we have two distinct groupings. This one would lead us to believe that we sampled from two populations. And then this is just really unusual. There's some kind of other thing going on there that if we took part of the graph, excuse me, part of the data out here, we probably could get a linear relationship, but we've got an awful lot of unusual stuff going on. If we saw a graph like that, we wouldn't want to apply the methods that we're learning in this section. Okay, so the first thing we're going to do is look at some scatter plots. And before I go to Statcrunch, I'm just going to show you one here. We'll talk about this problem and then we'll make a scatter plot. So this shows the amount of nitrous oxide explained by the amount of carbon monoxide in million metric tons over a 10-year period in the US. Select the choice that best describes any relationship between the variables. So let's take a look at the graph before we look at the answers. Let me get my Zoom balls out of here. There we go. So what do we see happening? So as the CO emission is increasing, we really don't see much going on. And then we do finally see some kind of a rise here. So do you think there's a negative linear association? So by negative, that would mean the points would be kind of along the line like this. As the CO was going up, the nitrous oxide would be going down. I don't see that. Overall, there's no noticeable relationship. There's a positive linear relationship. I'm not really seeing that. There might be something going on here, but overall, when I look at this, I just don't really see much of a relationship. And NO can be explained by CO. Remember, we don't want to talk about this correlation means causation. I can't explain one just because I look at a graph. So overall in this graph, I would say I don't really see a big relationship there. I mean, I just don't see it going on. All right, so let's take a look at, I'm going to do problem number 7. from your homework. So let me go over to my stat lab because I want to show you how to do. There we go. Okay, so we're going to go over to, this is actually 2.4. I know it sounds bizarre, but the scatter plot section is 2.4 in your book. So I'm going to go ahead and preview it. I'm going to look at problem number 7. So some of these problems will give you the scatter plot and some of them will have you create them. So this is one of the ones where you're going to create it. Okay. So it says the table lists weights in pounds and highway mileage amounts, MPG, for 7 automobiles. Use the sample data to construct a scatter plot. Use the first variable, weight, for X, and then we're going to use highway MPG for Y, because that makes kind of sense. Your X variable usually is the one we think somehow helps us explain what's going on and why. And it kind of makes sense. As the car gets heavier, we probably think the highway MPG would go down, would be my guess. Okay, so let's take a look at the data. Open in Statcrunch. And remember what the way they said to, oh shoot, I lost my Statcrunch thing here. Hold on a second. Here it is. Okay. Yeah, here it is. All right, so you want to go to graph. Scatter plot. And your X was going to be the weight of the car and your Y was going to be the MPG. And there's really not a lot of options on this, and just compute. So there's your scatter plot. It's actually pretty nice, pretty strong negative association. As the weight's going up, the miles per gallon are going down, which makes sense. That's what I would expect to see. All right, so let's take a look at the graphs they gave us and see which one. Well, it's not A, because A is showing a positive relationship. It's not B, because it's showing no relationship. So it could be C, it can't be D, it's got to be C, right? It's the only one that shows a negative trending, which is what
Are
we
both
expect.
of them interchangeable? Sorry
Wait a
about that.
minute. I got a different problem here. So I got a different problem. Hold on a second. Yes, I skipped ahead on the wrong problem. I'm sorry. That was looking at a different problem. We were on number 7. Sorry about that. Come back. There we go. There we go. Sorry. I skipped ahead to a wrong problem. It's this one here. It's still C. Sorry. I somehow skipped ahead on the problem when I made a mistake. Let's go back for a second when I was trying to find on my windows here. All right, let's try this again. Here's my output. Here we go. All right. So take a look. This looks just like it, right? From 2,000 to 4,000 or 5,000. Here we go. It's this one here. Yeah, sorry. I somehow clicked on the wrong problem when I went back into the homework. But it's got to be C because it's the only one that shows a negative trend. Because again, notice positive trend in A, nothing going on here. Negative trend, nothing really going on here. So it's got to be C. All right, so we got C. Is there a linear relationship between weight and highway mileage? Yeah, it looks like there is, right? As the weight increases, the highway mileage decreases, or as the weight increases, the highway mileage increases. There is a relationship. It's not linear, or there's no relationship. Well, we just said it. It's definitely a relationship. As the weight goes up, the highway mileage goes down, which makes sense. Okay. That's really all you're doing. Some of these give you the graphs and they're going to ask you to talk about what you see in them, and some of them you're going to create the graph. I don't really think you'll have trouble in this section. You don't have that many problems to work on. So we're going to come back to this in 10.1 also. So just hang on there for a second because we're going to come back to it when we start talking about the correlation coefficient. Because you're going to need Statcrunch to do that calculation for you. All right, so let's take a look now. So 10.1 now gets into the statistic that goes along with the scatter plot. And again, I'm going to skip over this because we kind of talked about this before, although I do want to talk about this. So the statistic that we use to describe the association between the two is called the linear correlation coefficient, and it's for the population, or for the sample rather, it's R. And it tells us the strength of the linear correlation between paired quantitative X and Y values in a sample. And it's computed. I'll show you the formula in a minute. You don't want to know the formula. It's terrible. What you need to know is your requirements. You need to have a simple random sample. You need to visually inspect it that you see some sort of a straight line pattern. And you have to worry about outliers. Okay, and outliers have to be removed because they really affect R. You might want to calculate R with and without outliers. And then just real quickly, so you'll appreciate why we use Statcrunch. Here's the formula for calculating the correlation coefficient. There's a lot of stuff in there, but we're going to use Statcrunch, so you don't have to worry about knowing the formula. But let's do the characteristics first. R is between -1 and +1. Okay, if it's -1, it means there's perfect negative correlation. As Xn is increasing, Y is decreasing, and it's all in a perfect straight line. If R is +1, we have perfect positive correlation. If any of the values of either variable are converted to a different scale, R does not change, which is a really cool thing to know. If you change your units on one or both, correlation coefficient doesn't vary. The value of R is not affected by choice of X or Y. If you interchange them in your calculations, you'll get the same answer. In the next section, that's going to make a big difference in regression, but here it doesn't make any difference. R measures the strength of a linear relationship. It's not designed to measure the strength of a nonlinear relationship, and it's very sensitive to to outliers rather. Okay, so let's just take a look at some pictures so you can kind of start to get a sense for what kind of correlation coefficient you would see. So it goes from -1 to +1. So this picture is positive correlation, and it's quite high. The closer R is to 1, the stronger the correlation. This has a correlation coefficient of 0.859. This one's very strong negatively. Correlation coefficient of -0.971. This one has no relationship, so we expect to see a correlation coefficient close to 0, and we do. And again, this one has a relationship, pretty strong, but it's not linear. So we don't get a large number here. We get a correlation of 0.33, but we shouldn't even have calculated because it's not a linear relationship. Okay, so it really doesn't even apply there. Let me see if there's a couple other warning things I wanted to bring up here about correlation. Let's see if we talked about all these. There is one thing you can do. I don't think we do anything with it in the homework, but I'll mention it anyway. If you take the square of R, it's called R squared, it tells you the proportion of variation in Y that's explained by the linear relationship between the variables. So we know that R is between -1 and +1, so R squared goes from 0 to 1. So the closer R squared is to 1, more of the variation is being explained by that linear relationship. I don't think I gave you any homework problems on that, but I did want to mention it. A couple common things here. Assuming correlation implies causation, I mentioned that before. Using data based on averages, this suppresses the variation and it's going to inflate your correlation coefficient, and then ignoring that you might have a nonlinear relationship. That's why it's so critical to make a picture before you do any calculations. All right, so we're just going to jump in and do a couple of problems in Statcrunch so you can see. Let's see, we're going to do problem 9 and 13. Get back over to Statcrunch. So you can see how these work. Oops. And push the right buttons. There we go. Okay. So now I need to go to chapter 10 and 10.1. And I pick number 9. You don't have that many here to do calculation-wise with Statcrunch. All right, so the first thing in most of the problems they're going to have you do is create a scatter plot. So we're looking at horsepower and expected gas mileage. So in the last section, we did weight of the car and the gas mileage. Now we're looking at the horsepower rating. So again, what would we expect to happen? As horsepower goes up, we would think that the miles per gallon would go down, right? That's what we expect to see. So let's take a look at the scatter plot. All right, so we're going to go to graph, scatter plot. And we're looking at using horsepower for X. Oops, I'm not up far enough, that's Y. Horsepower for X and gas mileage for Y. Compute. All right, so what do we see? We see 3 clumpings here really, but we see this looks like a somewhat linear relationship. But we have a grouping of cars here with low horsepower and they have high gas mileage. We have a middle group here, and then we have one car up here that's got a really high performance car, I guess, with horsepower of 310. There it is, where gas mileage is only 10 miles per gallon. All right, so let's take a look at the ones they gave us. All right.
Please,
so,
can you redo what you did to from the graph? Which option did you choose?
Sure. Graph, scatter plot, and pick your X and Y. Now in this section, X and Y are going to be important because you want to match up what the graph shows. So we're going to put horsepower as X and the gas mileage is Y, and then just compute. And here's your graph. All right, so let's take a look at the pictures. It's not C for sure. It looks like it could be A, doesn't it? We can pop it out here too. Yeah, there's the grouping of 3. There's the middle group, and there's the bottom one. So it looks like it's A. You might be able to read these visually yourself from the data table. I don't know. I can't. It's hard for me to see them that way. Let's check and see. Yeah, that's right. And then they want you to describe the direction, form, and strength of what you see. All right, so let's go back to Statcrunch. I can find my window here. All right, so what did we see here? There's a negative, right? Negative. I don't think it's curved. There are gaps in here, but I think it's just that we have groupings of cars with different horsepower. I don't think that's a big deal, but I do think on average it's negative straight, and it's actually pretty strong. Let's check it and see. Yeah. And now they want the correlation coefficient. Okay, so to do the correlation coefficient in Statcrunch, you're going to go to Stat, Summary Stats, and Correlation is one of the choices there. Remember, we used to do summary stats on columns. You're going to do correlation, and you're just going to pick the 2 variables. Click and then Control click to add the other one, and that's it. And there's your correlation coefficient. It's very strong, negative 0.917. Put that in here, negative 0.917. And let's see. What does the plot say about fuel economy? So let's go back and look at the plot again. Oh, where'd my plot go? Oh, I took it down. That's right. Actually, it's still here. You know, in Statcrunch, it keeps track of everything that you did. So let's go back here and look at results. So we had a scatter plot. There we go. So it says vehicles in the selected group with more horsepower have lower gas mileage. That's a pretty true statement. Yeah, it must be A. There's only 3 choices because we saw that in the picture. The higher the horsepower, the lower the gas mileage. And there's your final check. All right. And then I was also going to do number 13. Give you a practice on another one. You have a bunch of definition questions at the beginning, but okay. So this is domestic flights flown each year from 2000 to 2016. We want to find the correlation first. So let's click on this. Open up the data. Now, I would do the picture first, even though they're asking for the correlation. Let's go ahead and make the scatter plot first, because I really like to look at my data. So whenever you have a time variable, it's generally always going to be X, and Y is going to be the number of flights. Okay, so what do we see? We don't see a linear relationship there, do we? Interesting graph. All right, but let's do the correlation while we're here. So remember what we did, stat, summary stats, correlation. Pick the 2 variables. So I get negative 0.414. Now I think it's going to ask you a question about whether or not that you should have done that. Okay, so we got that right. And then they want the scatter plot, which we just looked at, right? It was this one right here. Did it really fall off in the last year? I don't remember that. Let me see. There's my Statcrunch window. Here it is. Back over here. Whoops. Oh yeah, there is an outlier right down there. I missed that right there. There's one that really fell off down there. So it must be B. Describe the trend. All right, so what can we describe here? Most of the points follow a straight positive trend line. Well, I wouldn't agree with that. Most of the points follow a straight negative trend line. Most of the points do not appear to follow any trend. One point is much lower. That's definitely something to comment on. The trend of the points does not follow a line with points first rising and then falling. One point is much lower than the other points. Again, this is a better answer. Okay, C is not incorrect, but D is a much better answer. Why is the correlation you found in part A not a suitable summary of the strength of the association? The correlation is not a suitable summary because the variables are quantitative. The trend is not linear, and there is at least one outlier. Okay, so the variables are quantitative, but we don't see a linear trend and there's at least one outlier. And let's see if there's another part to it. Yes. It turns out the value for 2016 was only for half of a year. What should we have done with that point? So that's kind of interesting because if I go back to my graph, if I double the number here, it would put it right back up here with the rest of the data. So that really helps to explain why it was so different. So probably that should not have been included. It was based on incomplete data. Yeah, probably shouldn't be included in either one because it's very misleading. Even on the, if you put it on the scatter plot, it looks like you think it's a valid data point. Yeah, so that's the right answer. Okay. All right, so you only have a couple calculation ones in here, 5 ones with calculations. The one in the beginning are definition questions, so I don't think you'll have any trouble with those. All right, so let's go on to the regression now. So what we're going to learn now is, now that we know that we have a linear association, how can we come up with the equation of the line that describes the data? Because usually when we talk about correlation and then get into regression, we want to actually use data to make some predictions. That's kind of the goal of collecting, oftentimes of collecting bivariate data. And so what we're going to learn in this section is to find the equation. If we were to fit a straight line onto the data on that scatter plot, what's the equation of that line, that best fitting line? It's called the regression line, the regression equation. It's also called the least squares line. And the regression equation is basically written like this. It's in slope-intercept form, those of you remember your algebra class. So we're going to predict a value of y for some value of x. We've got a y-intercept, which is what occurs when x is 0, and then we have the slope of the line. And the slope of the line tells us how much does the y variable increase for each change in x of 1 unit. Okay, and we call x the explanatory or the predictor variable, or sometimes independent variable. And then y with a little hat, like we had for the p hat, is called the response variable or the dependent variable. So we're trying to use x, whatever x is, to make predictions about y. Let's see, I'm going to skip over that there. You can read that on your own. So there's a lot of requirements for, again, similar to what we just looked at before for the correlation. We have paired data that's quantitative. The scatter plot shows a somewhat straight line pattern, and we want to worry about those outliers. Okay. Now, there's a lot of formulas here, but we're going to use Statcrunch, so we're not going to worry about those formulas. Generally, it says here, your book says that we round this y-intercept and the slope to 3 significant digits. It's really going to depend on the problem in Statcrunch and what they ask you for. A couple of things. If the model is not useful, if it looks to be a bad model, we shouldn't use it for predictions. If it's a good model, the scatter plot looks like there's a nice linear relationship, then it's a good thing to use for predicting. You only want to do the regression equation if you have linear association, and then R shows that there is a linear correlation. And then finally, you want to look at the scope. What values of x did you use to build your regression equation? You don't want to go ahead and do predictions outside those values, because we call that extrapolation. That's where you try to predict for an x value beyond the values that you use to build the model. Let's see. There's a little diagram from your book. I'm not going to go over that. And I talked about the slope. We'll work on the slope with some of the problems, interpreting those. A couple other important definitions. An outlier, we talked about outliers before, is a point that's far away from the other data values. It may be influential and it may not. Influential would strongly affect the graph of the regression line. So if the outlier is along the same line as the rest of the data, it probably doesn't affect it. But if it's really far away from it, it could really change the slope or the y-intercept. So you want to take a look at it and decide whether or not it should be part of the data, and should it even be included. And then residual, for every observed y value, we can predict, and the difference between those two is called the residual. And the reason I mention this is because when we do the regression equation, it is fitted in order to minimize the squares of these residuals. So mathematically, the regression line that we fit meets what's called the least squares property. It forces the sum of the squares of the residuals to be minimized, and that's the equation that we use. An interesting thing to know is that the regression line will always go through the point x bar, y bar, so the mean of the x's and the mean of the y. So basically what happens is the line gets placed onto the graph right there, and then it's rotated such that the square of these residuals is minimized. And again, mathematically, Statcrunch will do that work for you, but that's what the least squares regression line is. That's how they decide which is the best line. Let's see. We just talked about that. All right, so let's do some problems so you can see what you're going to be seeing in here. So you're going to be doing the regression equation and then sometimes make a prediction, and then they'll ask you to interpret. So I think I picked 2 problems to do. So let me go ahead and change my share here. Go back over to my stat lab. And now we're going to go up to, this is 10.1. Now we're going to go to 10.2. And the first one we're going to do is number 11. And these are pretty much all the same. All right, so first of all, they give you some data. And they're looking at, now we're looking at the chest size and weight of several bears. So what we want to do is people wanted to be able to use the measurement of the chest size. So if they're out in the wild and they're capturing bears, they can measure their chest so they don't have to take a scale along to weigh them. So they're trying to use the measurement of the chest size to predict how much the bear weighs. And we've got 6 bears that we measured. And so we want to find the regression equation. Okay, so what to do is open in Statcrunch. Now, it's critically important here that you pick the right X and the right Y, or you're not going to get the right regression equation. So you want to use chest as X and weight as Y. Okay, so you're going to go to Stat, Regression, Simple Linear. Pick your X. Remember, we said we're going to use chest. Pick your Y, weight. And in a minute, if you ever have to do a prediction, come on down here. Later on, when they ask you to do a prediction, you can put a value in here, like if the chest size was, I don't know, what kind of numbers do we have? I think it was something like 44. So if I put in 43 here, it's going to give me a prediction for a bear with a 43-inch chest. And I'll show you where that comes out. So you don't have to do that by hand. All right, so here's your output. Okay, here's your regression. It's the 1, 2, 3, 4th line down. Weight equals, here's your y-intercept, negative 227.27 plus 11.11 times the measurement on the chest. There's your correlation coefficient, 0.924. A nice thing on here, it also gives you a picture. So there's a graph of the chest size and the weights, and there's the graph of the linear regression equation that was just fitted to the data in red. All right, so we want to put in the regression equation. So let's take a look at the instructions. Round to 1 decimal place. So I'm going to put in negative 227.3. Negative 227.3, and then I'm going to put in, let's see, 11.1 times x, 11.1. Okay. Now here's the prediction part, 57 inches. Okay, so let me go back to my Statcrunch output. And by the way, I had done a prediction here, and here it came out for a chest size of 53, but we want to do 57. So let me go back and edit this and make the predicted value here. We want to predict for an X of 57. And if you scroll down, there's your prediction. 406.1 pounds is what we predict for that bear. 406.1. Oops. Okay. And basically what you did there, what Statcrunch did for you, it took 57 times 11.1. Let me show you in the calculator. So you could do it by hand, but you don't have to. So put in the size we wanted to predict for, 57 times the slope, 11.1, and then add 227.3. In this case, it's a negative number. And we get 4. So it's a little tiny bit different because of the rounding off here, because we rounded off so much over here. This one here is coming out with an unrounded values. It gives you a lot of latitude, but if you use the one from Statcrunch, it'll just save you a lot of work. Is the actual result close to the, is this result close to the actual weight? Off by 30 pounds. Say it's not
That'd be
very
no.
close. Yeah, I think it's not very close. Let's see what they say. Yeah, not very close. Okay. All right, let's do another one, number 14. These are all pretty much done the same way. Number 14. So this one is, oh, this is a big example from your book. He loves this.
Dr.
this is-
Rudy,
Yes. Mhm.
real quick, just for the regression line again. Just for the Statcrunch.
Uh-huh.
Can you just kind of walk through that just one more time?
Yeah, let's do it here on this one, okay?
Or is that-
They're all going to be done the same way. So Chris, I'll do one here. It's going to be the same thing. This is looking at
Okay, sounds good, thank
predicting
you.
the Nobel laureate rate for a country. They're trying to use internet user numbers to predict Nobel laureate rates. Kind of a bizarre thing, but and they want you to find the regression equation. So click here for your data. Open it up in Statcrunch. Okay, so go to Stat, Regression, Simple Linear. All right, then you want to picture X. So we wanted to pick the internet users to be X to predict the Nobel laureates. And then that's all you got to do to get the regression equation. And then just hit compute. All right, so here's your regression equation. Negative, here it is right here, fourth line down. Nobel laureates, the Y, equals negative 23.084 plus 0.453 times the internet users. You can also see it right down here in the little table. There's the y-intercept and there's the slope. If it's easier for you to read it off there, it's exactly the same. So let's go ahead, and they want, this one has a little different directions in it, by the way. It wants constant to 1 decimal, and the coefficient, that means the coefficients here, the second one to 3 decimals. All right, so your constant to 1 decimal would be negative 23.1. Negative 23.1. And then the other one, they want 3 decimals. 0.453. 0.453. All right, and I think there's some more parts to this one. Come on. Okay. And then we want to do a prediction again. So go ahead back and we want to predict for 79.7 per 1,000. Is okay, yeah, 79.7 we want to predict for. So let's go back to Statcrunch. Just go into your options and edit. And down here under prediction for Y, put in 79.7. Oops, 0.7 and then compute. And then your prediction will be all the way down here. So we would predict 13 point, what decimals? 1 decimal place. So 13.0. We would predict 13.0 for the number of Nobel laureates. 13.0. And then they're going to ask you a question about it. How does that compare to the country's actual Nobel laureate rate of 1.9? Well, that one's not very close at all, is it? Let's see, very close, not close, equal to, opposite to, not very close. Yeah, not very close. Okay. Okay, does that make sense, Chris? Did you see that? You okay now?
Yeah, I wrote it down. Thank you.
Okay, yep. And don't forget, you still have the videos over in, you know, if you forget when you get home, let's go back over to our course for a second. In the unit module, in unit 6 we're in now, you do have videos for all these. So unit 6, and you've got somewhere down here, Statcrunch videos. So you've got one for 2.4, 10.1, 10.1 would be just the correlation, 10.2 would be the regression, and then we're going to do this next one coming up here. Okay. All right. So I don't think you'll have trouble with those. I think that's all I picked to do. Yeah. All right. So correlation, regression, correlation coefficient, scatter plot, interpret scatter plot, and then regression, form the regression line, make a prediction. I don't really think you're going to have any trouble with the homework on here. It is important on regression that you pick the right X and the right Y. For correlation, it doesn't make any difference if what you pick for X and what you pick for Y. If you remember in Statcrunch, I don't think I have a Statcrunch window open anymore. Yeah, I do. In Statcrunch, when you go to do correlation, you go to stats, summary, stats, correlation, it doesn't even ask you for X and Y. It just asks you to select the columns because it doesn't matter which order they're in, but it makes a big difference for the regression equation. If you flip X and Y, you're going to get a completely different regression equation. The y-intercept and the slope will be different because you're trying to predict using the variables in the opposite form. So that's probably the hardest thing that students have to get used to. All right, so let's go ahead and go to the very last section. You're almost done. All right, and the reason we throw in this last section is because this is something, I know a number of you are going to go into nursing, but in any field, in many journals, authors will use the chi-square test of independence to analyze data that's in a contingency table. And if you remember way back when we did probability and conditional probability, we worked with data and contingency tables. They were two-way frequency tables. So we had rows and columns, and we have frequency counts. And now the data are categorized by categorical variables, not numerical variables. And we have at least 2 rows and 2 columns. And what we want to test for, again, we're looking to see, is there a relationship between the 2 variables? Are the 2 categorical variables somehow related to one another, or are they independent? Okay, and so we're going to look at a two-way frequency table. Okay, one variable is going to categorize rows and the other one's going to be in the columns. And we're actually going to do a test of independence. And the null here, this is the only time you have hypotheses without numbers. So our null is going to be that the row and the column variables are independent. And you name them. You'll say variable 1 and variable 2 are independent. That's my null. My alternative is either they're not independent or they're dependent. You'll see both words used. They mean the same thing, the opposite of being independent. When we do the hypothesis test and we reject, there's no direction this time. We just reject and say we have evidence that the 2 variables are not independent. They're somehow related to one another. And we're going to, the way we're going to conduct the hypothesis test is we're going to look in the frequency table, and using the assumption of independence, we're going to come up with what's called an expected frequency for each cell and compare it to what we observed. If it's very different, then we say that we're not seeing the proportions that we expected to see if they were independent, and that's going to give us a large chi-square value. If they're close to one another, we're going to get a small chi-square value. The requirements are random selection of data. We have to have frequencies in a two-way table. Every cell must have an expected frequency of at least 5. The sample data are independent of one another. And we also have a sample size less than 10%. These are not in your book. I've added these on because these are pretty commonly used. This independence usually comes along with random samples too. That's a pretty common thing. So here, our hypotheses are going to be this. The null is going to be the 2 variables are independent, and the alternative is going to be they are dependent or not independent. They mean the same things. And then you're going to have what's called a chi-square statistic for every cell in the table. You're going to take what you observed, subtract what you expected, square the difference, divide by what you expected, and then add those quantities all up to get the chi-square. One thing you will be asked to do in your homework is to find an expected cell frequency. I'll show you how to do that in a minute, which is just taking the row total times the column total and dividing by the grand total. And that gives you, if the 2 variables are independent, this is what we would expect to see in that cell. And this also has degrees of freedom, like we have with the t-test. So the test statistic has degrees of freedom. They're a little bit different. The degrees of freedom here are the number of rows minus 1 times the number of columns minus 1. So if you have a 2 by 2 table, it's going to be 2 minus 1 is 1 times 2 minus 1 is 1. It's going to have 1 degree of freedom. Chi-square test is always right tail. We reject the null when we have very large values of the test statistic, and the test statistic is always positive, by the way, because it's the square. So if you go back and look at it, when we add up to create the chi-square, you see we're squaring in the numerator, and the expected count is always positive. It's always a positive number. It can't be negative. Could be 0, but unusual. But it can't be negative. So they're always positive, and we're going to reject the null when we have a large value for the test statistic. And here's kind of a picture of what happens. And here's sort of a picture of what the chi-square looks like too. It's not a bell-shaped curve like a normal distribution. It's got a peak somewhere down here low. And then you're going to reject when you get very large chi-square values. So if your chi-square is down in here, which is a low chi-square, you're not going to reject the null. If your chi-square is very, very high, you're going to reject the null. And again, remember that if the p is low, then independence must go. Expected cell counts I mentioned before. And then conclusion. So again, if we conclude that the two variables are not, that we reject the null and that one is dependent on the other, we can't say what's happening. We can't say, well, this variable is causing the other one to increase. We can always just say that we have evidence that one variable is dependent or not independent of the other one. If we fail to reject, we say the evidence doesn't support rejection, kind of like we did with a two-tailed alternative. There's really not any direction to the test. All right, so some of the stuff we're going to do here by hand, and some of it then we're going to also go over to Statcrunch. So I want to get you familiar with the contingency tables first. So I picked a couple of problems from the book that we're going to work on by hand first. Okay, so a study of seatbelt users and non-users yielded the following random sample data summarized below. We want to test the claim that the amount of smoking is independent of seatbelt use. A plausible theory is that people who smoke are less concerned about their health and safety and therefore less inclined to wear seatbelts. Is this theory supported by the data? All right, so there's your data. So the first thing is the contingency table. Here's one variable. One variable would be wear seatbelt, yes, no. The other variable is number of cigarettes, and it's put into groupings here. So this would be non-smoker. Maybe you want to call this mild, moderate, heavy smoker, something like that. But they're into categories. So 20 people wore seatbelts and smoked 1 to 14 cigarettes per day. That's kind of how you read the table. All right, so we want to write the hypotheses. So when we write the hypotheses, we write down the names of the variables. So we're going to say cigarette smoking and seatbelt use are independent. Okay, so the names of the variables that we're using, and then we say they are independent for the null. For the alternative, just going to put ditto signs, so I don't have to rewrite the whole thing. We either say they are dependent, or an equivalent expression is to say that they are not independent. Okay. I kind of like this one because it's got the not in it that you're used to seeing in your alternative hypotheses from before. Your textbook kind of leans more on this one. These mean the same thing, but they're either independent or they're dependent or not independent. Okay, how many degrees of freedom are associated with this chi-square test of independence? Okay, so remember, degrees of freedom, row -1 times column -1, where R is the number of rows and C is the number of columns. So how many rows do I have here? 1, 2. I only count the row for a value of the variable that's being described in the rows, and the variables here are yes, wear seatbelts, or no, don't. So I've got 2 minus 1, and then how many columns do I have? 1, 2, 3, 4. So 4 minus 1, so I've got 1 times 3. So this table has 3 degrees of freedom. Now I want to find an expected cell count for no cigarette smoke per day and wears seatbelts. I'm going to cheat a little bit because I didn't put the totals on this table for you. I have them in my answer key. So let me go ahead. Oh, I guess I didn't write them down here either. Oh boy. All right, let's do them real quick. I thought I had written down the totals. Okay, you need the row totals and the column totals to work the problems. I think your problems in Statcrunch do that for you, but let's go ahead and do this real quick. 175 plus 20 plus 42 plus 6. So I've got 243 here. And I've got 149 plus 17 plus 9, 216. And I need a grand total, so I'm going to add those two together. And I get 459. And then we go across and add down the columns. 175 plus 149 is 324. And I can do that in my head, 37, 83, and 15. Okay, let's just check and make sure that adds up to the same total. 37 plus 83 plus 15, 459, yep, it checks. Okay, so I'm going to do no cigarette smoke per day and wear seatbelts. So I'm trying to do the expected cell count for this cell. Okay, so the formula for expected cell count, I've written it down here, row total. So I look across here and I say, how many total people are in there? 243. The column total for that cell is 324. And then I divide by my grand total, which was 459. Okay, so 243 times 324, and then I'm going to divide by 459. And I get 171, I'll just round it off to one decimal place, 171.5. So if wearing seatbelts and smoking cigarettes was independent, I would expect to see about 171, 172 people in that cell, and I have 175. So my observed is not really very far away from my expected. Now they went ahead and did the work for you. The chi-square is 1.36 with a p-value of 0.7154. At alpha 0.05, do we reject or fail to reject? So same rules that we did before for accepting or for rejecting or not rejecting. Would I accept or would I reject or fail to reject with this p-value and this alpha level? Is this less than this? No. So I fail to reject. Okay. So what does that mean? If I fail to reject, what do I mean? What am I going to conclude? Let's go back to our conclusion page. I have it for you. I had a little sheet there that showed you here. Oh, it doesn't show them on there. Shoot, I thought it did. Oh, I guess I don't have it shown in here. Okay, if you fail to reject, then you have insufficient evidence. It is in there somewhere. Remember, insufficient evidence to say that the two variables are not independent. Okay, so we can't say that they're not independent. We don't have sufficient evidence to support rejection of the claim that the two variables are not independent. So again, that same kind of wording that we used before on the hypothesis testing. All right, and then, okay, now I'm going to do some from the book, or from the homework, I mean, in my stat lab, yeah. Let's go get these up. So I just wanted to show you that one because I had a little calculation by hand in it. So let's go over to Statcrunch, or to my stat lab, and pull a couple up from there to work on. Number 7. So this is 11.2. We only do one section in chapter 11, which is 11.2. And that's the only one that's going to show up for you because that's the only place you have problems. All right, so I'm going to do number 7. And I picked this one because I think this is one of the ones, yeah, this goes back to reviewing some of the probabilities that we did way back in the probability unit before the midterm. So here's a table showing who survived the sinking of a ship. This is actually based on the Titanic, based on whether they were crew members or passengers booked in first, second, or third class staterooms. Complete parts A through G below. If an individual is drawn at random, what's the probability that they're a member of the crew? So it's a good review question. All right, so how many crew members were in this sample here? 873. Out of how many total people? 2171. Oh, no, I didn't want to do that. Wrong thing. I'm going to get my calculator. All right, so I'm going to take 873 and I'm going to divide by 2171. And they want a percent, so I'm going to go ahead and multiply by 100. And they want one decimal, so 40.2%. So 40.2% overall were members of the crew. What's the probability of selecting a third class passenger who survived? Third class, survive means alive. So we're going to take the 192 and divide by 192. Oops, sorry. Put in there 192 divided by 2171 and multiply by 100. So 8.8. 8.8. Now, before we go on, I just want to point out to you, let's look at this table for a second. Let's calculate the percents that survived in each of the 3 categories. Let's do the overall percent. So let's look overall and say what percent of people survived this sinking of this boat. So let me go back to my calculator. So let's take 721 and divide by 2171. So about 33%. So kind of keep that in your mind, 33%. Now, if the variables were independent, we would expect to see the same percent of people surviving in each of these groups. So let's take a look at the crew. 155. So I'm only looking at the crew column now. just like your conditional probabilities here. Now I'm down to, so I was at 30.3% for the whole table. Now I'm down to 17.8% if I look in the crew. If I then go to the first class passengers, what do I get there? 225 divided by 395, multiplied by 100. Now we see almost 57% of that group survived. Again, if the two variables were independent, we would expect to see the same survival rate among all these groups here, and we're not seeing that. So this is telling me that these two variables are probably not mathematically independent of one another. There's something going on here, which seems kind of reasonable, right? Because the crew would help all the other people get off the boat first before they got off, and so they would be more likely to die. Let's go to the next group. 149 divided by 355, 42%. And then the last group, third class, 192 divided by 548. Now we're down to 35%. So we're coming down here. So first class had the highest survival, second class, the next highest, third class. And then also notice crew had the largest number of members also and had the highest death rate or the lowest survival rate. What's the probability of selecting a random? Here's a conditional probability. This is what I just calculated this for you. Passenger surviving given they were first class. Okay, so this again is your conditional probability. So just first class surviving. We just did it 225 divided by 395. I think it's almost 57%. Yeah, 57% when I rounded off. 57%. If someone's chance of surviving were the same, regardless of their status on the ship, how many members of the crew would be expected to live? So this is where we're going to figure out an expected cell count for crew alive. So how do we do expected cell count? Row total times column total divided by overall total. So I'm going to take the row total for the crew that survived, 721. I'm sorry, these are people who survived first. 721 people survived. Multiply it by the number of crew members, 873, and then divide by the overall number of people on the ship, 2171. So I would expect to see 290 people, 289.9. I think that, oh, they went 2 decimal places. Hold on a second. 289.93. 289.93. So if the two variables were independent, I would expect to see in this cell right here, instead of 155 crew members, I would expect closer to 290 crew members had survived. Okay, state the null and alternative. Okay, so your null is always going to be the two variables are independent. So it could be A, and it could be C, and it could be D. And then what's the alternative? That they're either dependent or not independent. So it's going to be answer C. Survival was independent of status. It was not independent. Okay, now they want you to give the degrees of freedom. Row -1 times column -1. When you do degrees of freedom, the total row and column don't count. So we have 2 rows, so 2 minus 1 is 1. 4 columns, 4 minus 1 is 3. 3 times 1 is 3. 3. And then finally, I think you do the chi-square. Oh, they give you the chi-square. You don't have to do it here. So they gave you the chi-square and they gave you the p-value. It's barely greater than 0. All right, so if we test that, no matter what we test at, let's say 0.05, 0.01, it doesn't matter. Our p-value is basically 0. So are we going to reject or are we going to fail to reject? We have a very, very low p-value. We are going to reject. And we're going to say that there is sufficient evidence to support the claim that survival and ticket class are somehow related. Absolutely. Makes a lot of sense. Absolutely. Okay, so that was it for that question. I'm going to do one more. No, 2 more actually. Number 9. Let's do number 9. I'm going to get to one where you do the chi-square. Okay. All right. So this one shows the results of a study investigating whether after effects of epidurals administered during childbirth might interfere with successful breastfeeding. We are planning to do a chi-square test. How many degrees of freedom are there in this table? Okay, so again, you don't count the total column or row. So we have 2 rows, 2 columns, 2 minus 1 is 1. 1 times 1 gives me just 1 degree of freedom. The smallest expected cell count will be in epidural no breastfeeding. Why is that? Because it's got the smallest actual count in there. Okay, so we want to find the expected cell count for this cell right here. So we're going to take 468 times 398 and divide by 1184. So 468 times 398 and then divide by 1184. So 2 decimals, so 157.32. So I would expect to see in that cell a little bit more than 157 women. And I actually saw 180. Keep going. Oh, you don't even have to do this one. Okay. Now they just want you to check the conditions now. You should have a random sample. And so we're going to say that the babies are representative. That should be true.
Dr. Weaven, can I ask a fast question?
Sure.
Sorry, I don't mean to be repetitive. I don't know if this is already asked. But you're doing for degrees of freedom, you're doing rows minus columns.
Row minus 1 times column minus 1.
Rows minus 1
times column minus 1. Let's go back over to the notes. Make sure you see
Sorry.
the formula. That's okay. I want to make sure you get it. Let me get the
Alright.
page on the notes again.
because I thought I seen it, or I not.
No, it's in the notes. Hold on. Here we go. No, that's expected cell count. Wait a minute. I just did it. Where did I pull it? Let's see. Contingency table. Just went over it. Observe frequency. Hold on a second. All right, let's look through here because I know I went over it.
Yeah, no, you were talking about.
Oh, here it is, right here. Here it is. Degrees of freedom, row minus 1 times column minus 1. So see the parentheses? So you count the rows up, subtract
what it is.
1, count the columns, subtract 1, and then multiply those numbers together.
Sorry about that.
That's okay.
Roger, my bad.
That's okay. No, and when you get into the problems where you do the chi-square test, actually it'll show you in the output. We're going to do one of those in just a second. These are all just, I didn't realize I gave you all these reading ones, but let me go back for a second and we can finish up. Whoops, at the right place. Yeah, there we go. So what else? We had to less than 10%. We had to all the expected cell counts greater than 5. We had to have counted data. And we wanted to assume that everybody was independent. So we actually need all of these. That's pretty easy. All right, now let's do one where you actually do the calculation. So number 10. You have Statcrunch do it. No, you know, we did 10. No, we didn't. We didn't do this one. No, we didn't do this one. A poll investigated respondents' party affiliation based on the region that they live in. Test an appropriate hypothesis about this table, state the conclusions, and we're going to use a 0.05. Okay, so what are the first null and alternative? So remember, always is independent, so we can eliminate B. The alternative is either going to be not independent or dependent, so it's going to be A. Check your answer. And now we want to do the chi-square. Okay, so this is the first time you're going to see us do the Statcrunch work. So go ahead and open it up in Statcrunch. All right, so what you want to do is you're going to go to Stat, Tables, Contingency with Summary. Now you have to tell it where the data are. So your data here are actually, let me close this down for a minute. The counts are actually in these 3 columns here. These are the labels. So again, let me go back to this. Stat, Tables, Contingency with Summary. So I'm using the data in Democrat, Republican, and Independent, and then my labels in this case are in the first column, which doesn't have a name on it. You don't really need anything out of here unless you're interested. You could click expected cell count if you want. Here it is here. Here's your chi-square test for independence. It's the first option, and it'll always be selected already for you. And then just hit compute. That's really all you need. Okay, double check and make sure your table looks like the table you started with. Notice it's added on the totals here. Here's your chi-square, 4 degrees of freedom, because this has 3 rows. So 3 minus 1 is 2. Has 3 columns. 3 minus 1 is 2. So 2 times 2 gives me 4 degrees of freedom. Here's my chi-square here. Well, they want 3 decimal places. So 4.62 for the chi-square. And then they're going to want to know the p-value, 4.62. Oops. Shoot, 3. Missed it. I had the third one and I didn't do it. Hold on a second. Where is it? 4 point, it's not right. 4.6. 4.641. Sorry, I got that too.
4.6412. It actually rounds.
There we go. I got it. There we go. I didn't put enough decimals in. P-value. All right, so where's my p-value? Right next to it, and they want 4 decimals, 3261. And then they're going to ask you to interpret it, 0.3261. And what do we do? Okay, so the alpha was 0.05. So is this p-value 0.3261 less than 0.05 or greater than 0.05? It is greater, so therefore we fail to reject. And fail to reject, there's not sufficient evidence that these two are not independent. So that was C. And I think, oh, what am I made a mistake? Oh, I picked reject. Dumb. Supposed to be B. Failed to reject. Sorry about that, because it's greater there. Not sufficient evidence. Yeah, it's B. Sorry. Clicked it too quick. All right. So let me see if I had another one picked out. I have some more on the papers I want to go over, but so I do have a nice example. Let's do one more where you have to, yeah, let's do this one. We'll do one more where we use the Statcrunch. So most pregnancies are full term, but some are preterm, less than 37 weeks. Of those that are preterm, some are classified as early or late. A report examined those outcomes for 1 year and broke them down by the age of the mother. Is there evidence that the outcomes are not independent of age group? Okay, so you want your null and alternative first. So we're always going to say they're independent versus that they are not independent. Yeah, it's got to be A. And then they want the chi-square statistic. So let's just go right into Statcrunch. I think I have another Statcrunch open. Let me close it down so we don't get confused. Okay, Statcrunch. It's good practice for you to see another one. Okay, so we're going to go to tables, contingency with summary. Okay, now you want to pick the columns where the data are, and it's in early preterm and late preterm, and then your labels in this case are in variable 1. Labels just label the names of the rows, and then just hit compute. That's all you really need. And so here's your table. I always like to check and make sure it looks like the table they gave me, that something didn't happen. 129, yeah, it looks fine. Okay, and so my chi-square here is right here, 1.342. What they want? Yeah, 1.342, yeah. 1.342. And then they want the p-value, which is right next to it. How many decimals? 3. 0.719. Oh, you're going to get another one that's a not reject. I mean, fail to reject. Okay, so the p-value here, and we were using, they give me an alpha level. Pi square. Oh, wait, it's right down here, isn't it? Oh, I don't see an alpha level. Oh, here's the alpha level in the answers. Okay. So the p-value is, well, it's not less than 0.01, so it's greater than or equal to the significance level of 0.01. There's insufficient evidence to reject that null and conclude that they're not independent. A looks pretty good. It's not less than. Yeah, it's got to be A because the p-value is greater than alpha, so we have insufficient evidence to reject the null. Yep, there we go. All right, and then this is just an interpretation question. So you only have a couple where you actually have to do the work on this section. All right, I have one more on the paper I want to do because it's kind of an interesting one. I know a number of you are going already in nursing field or going into nursing, so I really like this last example that we have. And we're going to do it on a piece of paper. And actually, we'll put the data into Statcrunch too, and then we'll get the answer for the chi-square part. But let's take a look at this. All right, so, So here it is here. It says, alert nurses at the Veterans Affairs Medical Center in Northampton, Massachusetts noticed an unusually high number of deaths at times when another nurse, Kristen Gilbert, was working. These same nurses later noticed missing supplies of the drug epinephrine, which is a synthetic adrenaline that stimulates the heart. Kristen Gilbert was arrested and charged with 4 counts of murder and 2 counts of attempted murder. In seeking a grand jury indictment, prosecutors provided a key piece of evidence consisting of this table. Use a 0.01 significance level to test the claim that deaths on the shifts are independent of whether Gilbert was working. What does the result suggest about the guilt or innocence of Gilbert? All right, so the first thing you want to do is say, okay, so what are my null and alternative hypotheses? So what am I going to test here? I'm going to test whether Gilbert working, the null is going to be is independent of deaths on the shift, right? Because if there was no relationship between her working and then there being a death on the shift, you'd say they're independent. The alternative is going to be that these two, I'm going to say, are not independent. I really like using the word not because it matches what you learned before about writing alternative hypotheses with not equal to. All right, so unfortunately, I forgot to put this data in. Let me do it real quick while we chit chat a little bit. I forgot to set it up in, let me stop sharing for a minute. I have to get it into Statcrunch so we can work on it. So let me just take a minute to put it in here. So just take a second. So working, we'll have yes. Oh, whoops. And then death and no death. So we only have 4 cells in our table. So, and I actually want to show you something on this one before we get to the chi-square. 40, 34, 217, and 1350. Okay. All right, so let me go back to my share the screen here and go over to, all right, so I went ahead and I put the data in here for the problem we're working on now. So this is working, yes or no, and then whether or not there was a death or no death on the shift. All right, so the first thing I want to do before we do the chi-square, let's go into stat tables, contingency with a summary. And I'm going to pick, let's see what I have. Wait a second. Working death, no. Okay, I've got everything there. Let me go back in. Stat tables, contingency with summary. We're going to go death, no death, and then the labels are going to be working or not. And then let's take a look at, let's do row percents here. So what this is going to show me in the table is, take a look at the table. So the first row here is when Gilbert was working, and 15.5% of her shifts had a death, or the shifts on which she worked. When she wasn't working, only 2.5% of the shifts had a death. So it's kind of interesting data, isn't it? Looks like maybe there were more deaths when she was working. So let's take a look at the chi-square down below here. 86.48, and it's a p-value less than 0.0001. So do you think there is a relationship between when this person, Kristen Gilbert, was working and whether or not there was a death on the shift? Anybody want to take a stab at that? So we see it right here, 15.6% of the shifts had a death when she was working. When she wasn't working, it dropped down to 1/5 the level, less than 3% when she wasn't working. Oh yeah, there's something going on there. Highly significant. Okay, so just to talk about, this is a true story, by the way. She's actually in jail now. I think she's still alive. This happened in the 1980s in Massachusetts, and she was convicted. And there were more deaths on her shift as evidenced by the data that you see here. So this was 15.5% rate. And this one was, what do we say, like a less than 3% rate. So if you look at the difference between the rates of shifts with death when she was working, when she wasn't working, is a huge difference. And so the data does suggest the guilt of Gilbert. And like I said, she was convicted, and I believe she's still in jail, in prison in Massachusetts. So this is an example of how chi-square test might be used to show whether or not things in a contingency table show a significant relationship of two variables. So this is a highly significant. Remember, the p-value was less than 0.0001, really, really tiny. So it's extremely unusual if this would happen by chance, if in fact the variable of her working is independent of deaths on the shift. It does appear that there's a relationship between the two. So I'd like to finish up with that example because it's a pretty interesting one, and it's real data. You can Google her if you're interested. She killed a lot of people. Okay. All right. So that is it. Let me just stop sharing and see where we're at. Okay. So we still got time. All right. So questions from tonight. So we did a lot of stuff tonight, but I don't think you're going to have trouble with it. I really don't. You did correlation, scatter plots, regression, and then the chi-square test of independence. And there's not a lot of problems in each section. And they go together because you're looking at relationships between two variables, either quantitative with correlation and regression, or between categorical with the chi-square table. So I kind of think it's, even though it seems like they don't go together, they really do. And then that's the end of the material for the course. The assignments from tonight will be due next Wednesday night, which I know is kind of weird because that's also when you have to finish up your final, but with summer, it's just so hard to get everything in and, you know, give you sufficient time for the final. So your proctored final will open on Monday, 12:01 a.m. and be available until Wednesday night. Your stuff is due next Tuesday. Did I say Wednesday? Your stuff is due next Tuesday by 11 o'clock. So you have 4 homeworks and the unit 6 tests due next Tuesday by 11 o'clock. And then your final must be done by Wednesday night at 11 o'clock. All right, so questions from anybody? We did a lot of stuff tonight. So I will have class next week and I will post a copy. Let's go in real quick and just take a look. Remember about that. You have that preparation quiz that you can use to help you get ready for the final. Let's take a look at that real quick. Close this down. And let me go back up here to the main menu. So you have, let's do that. So here's your final exam preparation quiz. And remember the first question, I don't remember what formulas I gave you, but you have some formulas. Oh, you have a Z formula. There's the expected cell counts there. There's the residual formula, the regression formula. The chi-square you're not going to have to do by hand, but I did give it to you there. And then your problems are in the same order that we covered the material in the course. So, and there's more questions on this than there are on the actual final. You have 36 questions on your final. But I urge you to use this to help you get ready. You will not have Statcrunch, remember, during the proctored final, just like from the midterm. So when it comes to things where you need to use Statcrunch, I don't remember where they are. I'm trying to find a question randomly if I can get to one where I gave you some output. Nah. Some of them have some output in them and you're going to read off of the output. Oh, there you go. There's one with output. Okay, so I gave you the confidence interval and I asked you to using a confidence interval to interpret, to give a decision about a hypothesis test. So the output is included in the question. There's one with a scatter plot in it. You won't do oh, looks like you got that one twice. There's another one with the scatter plot included and some output in it, like we went over tonight. So you'll be given the output when you need it to answer a question. You won't need Statcrunch. Okay, so you don't have to remember what to do to get the answers. All right. So I will post a copy of it. I'll generate a copy by the weekend and post it up there in the news item for next week. And we'll go over that copy together during class on Tuesday. All right. Okay, questions as we finish up. We have some time left. Anybody have questions they want to go over for their homework tonight or questions on things we did tonight?
Real quick, the test, it keeps the highest that you score, correct?
Yes. Which one are you talking about? I mean, for your unit.
The one that's due tonight, the unit test?
Unit test, yeah. If you take it again, it'll take I'll take the highest score.
Okay, where's that?
So it doesn't hurt you to retake it.
Yeah, I plan on doing that. Thank you.
No, it doesn't hurt you to retake it because I'll take the higher score. And remember, for the preparation quiz, you can take that over and over again. So try to get above 70, try to get above 80, because then I'll add 5 points to your final grade. So I urge you, if you have time, to do that, to see that you can get a higher score on that, because that'll really help you get ready. And you'll also see how the questions are going to be presented. So when you're sitting for the final, you're not seeing them for the first time, because it is a little bit different than your homework because you're not using Statcrunch. You do need a calculator though, because you will have some things to do with a calculator. So you want to have a calculator with you. All right, everybody's so quiet tonight. Jeez. Wow, is it raining at anybody's house? Boy, we had a big storm here before class started. Thank goodness it moved over before we started class, but it was really crashing away.
Dr. Weidman?
Yes.
I was late to class. I just want to make sure that if you took attendance that
No,
I
I don't take attendance, Madison. Only those couple of weeks I mentioned. I don't take attendance now.
Okay, I just
That's
want to
fine.
make sure.
No, you're fine. You're fine. I'm just glad you came. No, I only when I have to, because you should 5